ideal gases. Now let's talk about gases in a very particular case, where we have a species that approximates what we can call an ideal gas. Most of what we will consider in this chapter will be ideal gases. At the very end of the chapter, we will discuss non-ideality a bit, but it will be a very small portion of our discussions. We will first define an ideal gas. Since actual gases are not real gases, we need to discuss when we can treat them as such. Let's first start with the definition of an ideal gas. In an ideal gas, molecules move completely randomly. They do not interact with themselves or anything else. When the molecules collide with themselves or the walls of the container, they do so elastically. An elastic collision is one where all of the energy is conserved. Think about if you have a perfect bouncy ball and you collided it with another perfect bouncy ball. They'd bounce off each other and fly off with the total kinetic energy being exactly what they started with. Now, the last thing that we need to focus on is that molecules are point masses, or in other words, that each atom has zero volume. Of course, this doesn't mean that the gas as a bulk system doesn't have a volume, but think back into 1A when we talked about atomic radii. That gives us an approximate volume of each atom. An ideal gas does not have this volume. It has a zero volume for each atom. Generally, we will use this system at low pressures, such as around atmospheric pressures, and relatively high temperatures. Typical room temperature is plenty high for most gases to behave ideally. Now let's talk about these two conditions for ideality. Why would low pressures and high temperatures lead to gases acting more ideal? We'll start with low pressure. Remember what I said about ideal gases not having a volume. Imagine that you put 3 people in a very, very large lecture hall. What percent of the total volume of that lecture hall is made up by those 3 people? It's of course going to be something very small or very insignificant. Now, what if instead I put 400 people in a large lecture hall? This is going to make up a significant amount more of the volume. And perhaps if I put 1,600 people in a lecture hall meant for 400, now the people are stacked on top of each other. As we increase the number of students in the lecture hall, even if all the people are the same size, the percentage of the volume taken up starts to increase. This is going to be the same idea when we start putting atoms into a container. At first, if there's only a few atoms, the percentage overall will be very small, and the volume of the atoms will not take up a significant amount of the container. But as you increase the pressure or you increase the number of atoms in the container, now the volume of the atoms start to become a bigger deal. They become significant, even if the atoms are the same size as they always have been. Keeping a low pressure means less atoms in a given volume. This lowers the total percentage of the volume taken up by the actual space caused by the atoms. Now let's look at temperature. If you and your friend are both rushing to classes on opposite sides of the campus in a huge hurry, and you run by each other, how much interactions are you really going to have? A quick nod? A wave? Are you going to stop and hug and catch up on the past years of your relationship? Now, what if instead you're slowly meandering toward your classes during a 4-hour break? Now how much interaction are you going to have? While this might be a silly analogy, it will help you to understand why molecules at high temperatures are more ideal. The higher kinetic energy, or the speeds, of the molecules mean that they will be able to overcome most interactions that are occurring between them. If you slow them down by lowering the temperature, they won't be able to overcome these interactions. We won't really get into intermolecular forces until next chapter, but this bulk property concept can be understood without delving more deeply into it. In review, an ideal gas has elastic collisions. It's a point mass, or in other words, has no atomic or molecular volume. It has no interactions with itself or its container. Of course, the gases that we deal with in real life are real gases. However, the ideal gas approximation will work well at high temperatures and low pressures.